All right, practice problem number 1 associated with sample problem D. So here we're actually going to be dipping back into our kinematic equations. So you'll need to reacquaint yourself with those 4 kinematic equations. We're going to really focus on one right now, but hopefully this comes back to you pretty darn quick. Now the reason that you're going to have this kinematic equation come back to you is because we are going to be solving for things like delta x, delta y. We're going to be using acceleration due to gravity because we're talking about delta in the y direction. So here we go. A baseball rolls off of a 0.70 meter high desk and strikes the floor 0.25 meters away from the base of the desk. How fast was the ball rolling? And so what I'm actually going to be solving for is a velocity. Okay, now it was rolling on the top of a desk. Okay, so we could call this its initial velocity, but we can also consider this to be velocity in the x direction because there's no initial velocity in the y direction. Okay, so if you look for help on this particular type of problem from other sources, you need to be on the lookout for either of these representations because they're both pretty interchangeable. I'm going to try to be as clear as I can, but hopefully it doesn't confuse anyone if I kind of kick back and forth between these two, because the initial velocity is only velocity in the x direction. Okay, so I hope you guys don't get confused there. Okay, here we go. So let's establish our coordinate system. Okay, so we got plus plus, minus minus. Now let's actually draw our situation here. So we have, say, a tabletop, okay, and then desk goes down. So what we have here is the y direction, and we also have the x direction. Okay, this is 4 perfect right angles, by the way, if you guys can't tell. I know it's not the highest quality recording, but that's perfect. It's absolutely, it's like it came out of a printer. And so the things that we know here, we have a delta y of 0.70 meters. And we actually have a delta x of 0.25 meters. Okay, so we have some information. Now, we also have, might not look like it's not listed in the problem, but we also have acceleration. Now, the ball was already rolling, so I'm not talking about acceleration like that initial force, that initial push that got the ball rolling. We're talking about once the ball actually rolls off of the desk and hits the ground. So the only acceleration that's acting on this ball here, on this baseball, is acceleration in the y direction. We know that that is equal to g, right? But it's in the negative direction, so it's got to be a negative g. So that makes the acceleration in the y direction negative 9.81 meters per second squared. Okay, so we have quite a few givens from the problem. So let's draw our situation here. So we have acceleration in the y direction that is going down. Okay. We also have this distance. Okay, we have the delta y. Okay, so this is the delta y is equal to 0.70 meters. We also have the delta x, which is 0.25 meters. All right, so we have our situation. Let's see what we can do here. So I'm going to look through the kinematic equations. I'm going to need to find something that has a displacement right? Essentially delta x or delta y, I mean, they're interchangeable because you can talk about it, that, you know, the kinematic equation representing horizontal motion or vertical motion, doesn't matter, but we need a displacement. We're going to need a velocity, specifically an initial velocity, and we're going to need something that will use acceleration. And so the equation that I'm going to start using here, hopefully this looks familiar to you. If not, you're going to need to kind of reverse yourself in the kinematic equations. Okay, so we have displacement is equal to initial velocity multiplied by time plus 1/2 the acceleration multiplied by time squared. Now, in the x direction, okay, we have initial velocity. The ball is definitely, you know, in motion for a set amount of time. But in the x direction, there is no acceleration. Acceleration is 0. Okay, so anything multiplied by 0, it does not matter what this time interval is. Okay, this whole side of the equation cancels out. So it turns out that my delta x, which is this displacement, is equal to, again, velocity. Okay, I'm going to do this. Hopefully it doesn't screw you guys up. That velocity in the x direction multiplied by the change in time. Okay, I'm hoping you guys are okay with this representing the same thing. Initial velocity is velocity in the x direction. But I don't have to bring across the rest of this equation because that acceleration is 0. Okay, it's moving at a constant speed, right? It's just rolling, and then once it's in free fall, there's no force causing it to accelerate in the horizontal direction, only y direction. So, but we can do the same thing in the y direction. So we can the exact same kinematic equation to describe motion in the y direction. But as the ball was rolling across the desk, there's 0 movement in the y direction. So there is no velocity in the y direction. So this initial velocity ends up being 0. And again, it doesn't matter what the time change is. Anything multiplied by 0 is 0. So you can actually get rid of that half of the equation. So I end up with 1/2 acceleration times change in time squared. Now the thing that's useful about setting up these two equations here is that both of them include time, and the time for both of these equations is going to be the exact same time. Right? It's the time that the ball was in free fall. Okay, that's the time that it took the ball to travel this 0.25 meters in the x direction. It's also the amount of time that it took the ball to travel this 0.70 meters in the y direction. So the time is the same. Okay? We're not actually worried about the time of the ball when it was still on the desk. So time is going to be the same. Because delta t is going to be the same in both equations, that's going to allow us to do some substitutions to actually set this up. Now, in order to substitute for delta t, let's actually solve for delta t. Let's see here. So, we know that, give us more space down here. We know that delta y is equal to 1/2 acceleration times the change in time squared. Now, if I'm going to solve for t, what I'm going to have to do is divide both sides by acceleration. Okay, that'll cancel. I can multiply both sides by 2, right, to get rid of that 1/2 that's multiplying there. And so just as a quick in-between, at this point, see what would I have? I'd have 2 delta y divided by acceleration is equal to delta t squared. Then I'd have to square root both sides. And I would end up with a rearranged solution for time that looked like 2 delta y over acceleration all under a radical. Okay, so in this equation I have over here for my my delta x, right? Because again, I'm actually trying to solve for this velocity in the x direction. I can actually take this value for time and substitute it in here. Okay. Now before I do that, let me actually solve for velocity in that x direction. Okay, so I guess this would be pretty simple. Divide both sides by delta t, and I'll end up with velocity in the x direction is equal to delta x over delta t. So I know that I can take this expression and substitute it in for that delta t. Now when I do that, for simplicity's sake, actually let's just do it. Just do it and see what it looks like. All right, so here is a bunch of stuff. Now at this point, we've solved for velocity in the x direction. At this point, we have, in this solution for velocity in the x direction, we have 3 terms that we have values for, right, given to us by the question. And if you wanted to, you could actually plug those values in to this equation as it exists right now. Okay, but for the sake of having it look not quite as gnarly here, I'm actually going to do a little bit of a rearrange so that it's easier to kind of plug stuff in. So I hope you guys understand that we're dividing delta x by, you know, like a fraction, right? We have a numerator and denominator. When we're dividing by a fraction, when you divide by a fraction, it's the same as if you were to be multiplying by the inverse of that fraction. Okay, so this would actually be represented just as well by acceleration divided by 2 delta y. Again, this is square rooted, and then multiplied by that delta x. I like to do it this way simply because what I have to plug into the calculator ends up being a lot easier. Okay, that's it. That's the only reason. There's no other reason. So you could actually have stopped right here, plugged in your values. As long as you were careful with your calculator work, you get the exact same answer. But I like to do it this way because it's a little bit easier on my calculator. Got my acceleration on top, divided by, okay, so it's 2, and then my delta y from the question, 0.70 meters. That is still square rooted, don't forget about that. And I need to multiply by delta x, which again from the question, 0.25 meters. Once I get that into my calculator, making sure that I use the appropriate number of significant figures. Question has me using 2 sig figs, so my answer is going to have 2 sig figs. So looking at what calculator gives me, I'm going to go with 0.66 meters per second. Okay. Again, quick recap. I needed to solve for a velocity in the x direction. In order to do that, I needed to have something that I could plug in for time. And so I used the information, information in the y direction to solve for time, right? That's why I used my delta y here. Okay, so the time that it took to actually travel that 0.7 meters in the y direction, because that time is the same amount of time that it's going to take the ball to roll, travel that 0.25 meters in the x direction. These times are the same. And because I rearranged this equation to look like this, I could solve for delta t and actually have a term that uses stuff that was given to me from the equation. Now, once I had this solved for delta t, I could actually plug that in for delta t, because we don't know how long this thing was in the air. We didn't know how the baseball was in the air. So we do not have the ability to simply plug that into the equation, right? I mean, check me if I'm wrong, but there's no time given in the question here. So we don't actually have a value for time, but we can rearrange it to represent time in a way that uses two terms that we do have from the question, right? Delta y and acceleration. Once we did that, we could substitute this entire expression in for delta t here. And again, once we get to this spot, we've actually solved for velocity in the x direction, and we've solved it in a way where we're actually using the three we can actually take from the question, the way the question's worded. Once we do that, it's just some calculator work. You come up with 0.66 meters per second.